Part 1. Origins and Technological Evolution. 1. A brief history of flying car concepts. Since the dawn of motorized transportation, the dream of flying cars has captured human imagination. The idea of personal aerial vehicles emerged as early as the 1910s, shortly after the invention of the airplane and the automobile. Science fiction media in the 20th century, from The Jetsons to Blade Runner, helped entrench the concept as a symbol of futuristic living. The first functional prototypes were developed in the mid-20th century. Notably, the Convair Model 118 in 1947 was a hybrid vehicle with detachable wings, though it failed to gain traction due to safety issues and impracticality. Other attempts, such as the Mahler Skycar in the 1990s and the Terrafugia transition in the 2000s, signaled growing technological ambition but were hindered by regulatory and logistical barriers. 2. Early prototypes, from vertical takeoff to eVTOL. The concept of VTOL, vertical takeoff and landing, became a pivotal breakthrough in aviation technology. Originally used in military aircraft like the Harrier jet, VTOL gradually transitioned into the civilian innovation space. By the early 2020s, a new class of flying cars known as eVTOLs, electric vertical takeoff and landing vehicles, emerged. Companies such as Joby Aviation, Lilium, Volocopter, and EHang led the race, introducing compact, autonomous, and eco-friendly aircraft designed for short-range urban travel. eVTOLs distinguish themselves through their electric propulsion, which drastically reduced noise and emissions. Using multiple rotors and advanced navigation systems, they promise safe, accessible, and efficient air mobility. 3. 2020s to 2040s, the breakthrough decade. Between 2025 and 2040, flying car technology underwent exponential transformation. Artificial intelligence, advanced battery chemistry, and smart infrastructure converged to make mass adoption viable. The 2030 World Urban Mobility Accords created unified air traffic regulation systems, enabling real-time sky navigation management. Breakthroughs included solid-state batteries that allowed longer flight duration, AI co-pilot systems that made autonomous navigation safer than human operation, ultralight nanomaterials that reduced vehicle weight without compromising safety, skyport hubs integrated into skyscrapers and suburban centers. By 2045, flying cars were a common sight in megacities like Tokyo, Lagos, Sao Paulo, and New York. Governments issued aerial driver's licenses, air lanes replaced highways in parts of urban centers, and sky-based delivery systems outpaced ground logistics. Part 2. How flying cars work. 4. Propulsion systems, electric turbines, maglev, and hybrid engines. At the heart of the modern flying car is its propulsion system. These have evolved significantly since early combustion engine prototypes. The most prevalent system today is the electric turbine, powered by solid-state or graphene-enhanced batteries. These turbines provide quiet, efficient lift and forward thrust without the emissions typical of traditional jet engines. Some experimental models use magnetic levitation, maglev, in combination with drone-style lift rotors for smoother and more stable urban travel. Maglev systems require infrastructure enhancements, such as electromagnetic highways or launch rails, which are being gradually implemented in high-density zones. Hybrid engines remain in limited use, combining a small combustion engine with electric propulsion for extended range. However, advancements in wireless charging and battery density are quickly phasing out hybrids. 5. AI piloting systems and autonomous navigation. Autonomous flight systems have become standard in flying cars post-2035. AI co-pilots perform route optimization, collision avoidance, and dynamic traffic rerouting. These systems are trained on massive datasets and updated in real time through global air mobility networks. Each vehicle comes equipped with a multi-sensor array: LiDAR for terrain mapping, radar for object detection, GPS and quantum positioning systems for global navigation, atmospheric sensors for real-time weather adaptation. Autonomy levels range from semi-assisted piloting to full AI-driven flight, depending on regional regulations and operator preference. 6. Materials, design, and energy efficiency. Modern flying cars are built from ultralight nanocomposite materials. These include carbon fiber reinforced polymers, aerogels, and graphene-infused alloys that offer high strength-to-weight ratios. Some vehicles even feature morphing wings and adaptive body panels that change shape mid-flight to reduce drag. Aerodynamic efficiency is paramount. Advanced design software utilizes AI to optimize every curve, vent, and surface in real time. Many vehicles are modular, allowing conversion between passenger mode, cargo mode, and medical response mode. Energy efficiency is enhanced through regenerative braking in both vertical and horizontal movement, solar recharging skin panels, and AI-optimized route management. Some top-tier models even integrate hydrogen fuel cells or micronuclear packs for inner-city range. Part 3. The new skyscape. 7. Urban air mobility infrastructure. The rise of flying cars has reshaped city planning and urban development. No longer constrained by ground-based traffic systems, urban air mobility (UEM) demands new forms of architecture and civil engineering. Buildings in major cities now include aerodecks, multi-level skyports that serve as takeoff, landing, and maintenance hubs. Municipalities have adopted vertical zoning, allocating certain altitudes for different types of aerial activity. For instance, 50 to 150 meters, personal flying car travel. 150 to 300 meters, commercial cargo drones and high-speed air taxis. 300 plus meters, long-distance aerial freight and emergency services. Skyways, similar to digital highways in the sky, are coordinated by AI traffic control towers that ensure precise spatial separation and flow regulation. 8. Skyports, launch pads, and charging hubs. Skyports are to flying cars what highways were to automobiles. These hubs combine function and aesthetics, equipped with automated landing pads, rapid charging stations, cargo transfer arms, and biometric ID scanning systems. Charging infrastructure has evolved to include ultra-fast wireless charging plates, solar-backed supercapacitor banks, swappable battery bays for long-haul aerial vehicles. In suburban and rural regions, smaller sky pads have emerged, serving as personal or shared launch zones. Integration with existing transit systems enables seamless multimodal travel from air to ground and vice versa. 9. Regulating the sky. Digital lanes and drone corridors. Air traffic is now regulated by the Global Sky Grid, a quantum-encrypted, AI-managed system that communicates with all airborne vehicles in real time. This system manages route assignments, obstacle detection, altitude layering, emergency rerouting. Each vehicle's unique ID broadcasts position, velocity, and intent to nearby craft via mesh networks. AI adjudicates priority based on traffic flow, emergency status, and environmental conditions. To separate commercial and personal aerial vehicles, dedicated drone corridors exist, elevated above residential zones. Surveillance systems embedded in atmospheric beacons monitor for violations, unauthorized flight patterns, and vehicle malfunctions.